want to show you something before we actually do our lesson for the day. And it used to be something that you guys knew before you kind of took my class, but it's been lost over the years. So I'm going to draw a line here. And I'm going to duplicate it so I know the line I'm drawing here is exactly the same size. Now, I want you to imagine that this represents a piece of string, and I've put a pen at the end of it here, and then I've affixed the other end there so I could draw a circle. Does that make sense? So if I put my pen here and just like a compass, come along, just move along with the cord, I'll create an arc length on the piece of paper. And that arc length, S, will be, the length of it will be based on how big my displacement is and how long the piece of string is. Agree with that? Okay. How are those three things related? I taught you this. So if you don't remember it, then that speaks about what all of Q3 was about. But if I wanted to know S in terms of L and theta, how would I write it? Go ahead. Yeah, it's just a bridging equation, right? So S equals theta times L. Now, I could also turn this into a right triangle and drop an altitude here. I'm trying to be as clear as possible. I'm trying to get that right there at the end. If I wanted to determine the height of this new right triangle I've just created, how would I do that? Yeah? Okay, so H would equal sine theta times L. How close are these two numbers? Is it clear that it would depend? Like, the smaller theta is, the closer those two numbers probably are. Because if I repeat that a little bit, say for that angle, is it clear that this version of S is going to be much different than this version of H? Right, those two are going to be definitely very different. You guys agree with that statement? So when are these two nearly equal? Let's prove it. I think we can kind of get an idea. So here's what I want you to do in our 7 tables. So I'm going to choose 7 of you, or I'm going to choose something for each table to do. So let's see, table number, we got 1, 2, 3, 4, 5, 6, 7. Let's say angle in degrees, angle in radians, and the sine of our angle. So let's start with 2 degrees, 5 degrees, 10 degrees, 15 degrees, 25 degrees, 35 degrees, and 50 degrees. All right, so it's going to go table 1, 2, 3, 4, 5, 6, 7. I'm going to call out each table. You tell me the 2 numbers that would go for the angle when converted to radians, and then the sine of that angle. Give you, 30 seconds? 0.03488. Tell me the sine of 2 degrees. 0.34899. I'm sorry, 0.3034. All right, table 2.
Uh, 0.0873.
0.873. Give me one more number.
Oh, 0.08726.
And the sine of 5 degrees.
I didn't go any digits before past it, but I have 0.57357.
No, you don't. 0.057? No.
I have 0.57.
That is not the sine of 5 degrees. I believe you may have been making a mistake. 0.087. Okay, table 3.
We got for the radians
0.1745. And then can you tell me what the sine of 10 degrees is?
0.173648.
All right, table 4, 15 degrees.
For the radians, we got 0.261799, and then for the sine of 15, we got 0.25881.
Table 5. 0.4363323. 3323. All right. And sine of 25 degrees. Table 6, 35 degrees.
Sine is 0.573576.
0.573576.
3576.
And 35 degrees to radians.
The radians, that's point. .428.
I know it's not right. I'm giving you a hint where to start.
0.67258.
And 50 degrees.
0.872665.
And sine of 50 degrees.
0.766044.
Thank you. Whoa. And it's not necessarily easy to do, but it's not particularly hard. But again, to determine if something's in simple harmonic motion, you could do so experimentally by seeing if the motion of the object can be fitted using a sine or a cosine function. Now, I want you to be able to do better than that. I think you should be able to predict whether an object will behave with simple harmonic motion. But you can always measure it. The second parameter, what are the controlling parameters for your oscillator? Those controlling parameters are going to be something physical about the object you can change. That will control the parameters of oscillation. I'll remind you, the parameter that we're really looking for is omega. Omega is the controlling parameter for our oscillators. For the spring mass oscillator, we know that it's the square root of k over m. But there's something about that, about where we got that and how we got that I need you guys to be able to complete. It's not super bad, but what I found, especially today, is that students don't really understand what I mean. But just 2 days ago, 2 lecture days ago, we derived this from a second order differential equation. I won't say it was simple, but I would say that we derived where this came from by looking at a straightforward second order differential equation. Well, that's a lot of complex work, and I don't want to have to do it the same way every time. If you don't remember what we did, the first thing we did is we did a Newton's law evaluation. We applied the force concept model to a spring mass system. There was only one force, and so when we did that, we set that unbalanced force equal to MA. The next thing we talked about was Is the unbalanced force a restoring force? And that's really asking, is the force in the opposite direction of the displacement? If it is, you can go on to the next one. If it's not a restoring force, then there's no harmonic motion, so no point in going on. Step 3 is a little bit more complicated, but not much. You need to create a second-order differential equation. Now, we evaluated that here. We said, yes, this was a restoring force because the force was back towards the origin. So if we have a displacement to the left, the acceleration was to the right, and vice versa. We replaced A with our second-order differential with respect to position. And we solved for our second-order differential. This was creating our differential equation. And now the final test is, do you have a second-order differential equation that has a negative sign, a collection of constants, and the original function? That's what this is. You're looking to see if, or I'll say, do you have? That's what we're looking for. Do we have a second derivative that is equal to a constant times the original function? If we do, the constant is equal to omega squared. That's the set of things we did. At the end of the day, we're able to get omega. Omega is the controlling property. There are some clues, and I'm going to give you the first clue, is that generally, whenever you do this, the top part will have reflections of the restoring force, and the bottom part will be about inertia. That's what you should see. It's going to be a fraction, and you're going to have some stuff on the top that's going to be about the restoring force, stuff on the bottom that's going to be about the inertia. Making the top bigger makes it oscillate faster. Making the bottom bigger makes it oscillate slower. That's almost always what you're going to see with most of these simple harmonic oscillators. Right. Our pendulum. Step 1, apply the force concept model. Okay. I believe there are two forces acting on the system. I'm going to make a couple of labels here to give me some things to use. I think there's going to be a downwards force due to gravity. I'll label that mg. And I think there's going to be a force along the cable due to the string, and I'm going to call that tension. I have to choose a coordinate system. I'd like my coordinate system to be aligned with the direction of the acceleration. I do not think it's accelerating this way. I think it's accelerating this way. It's constrained to go in only one direction. So I'm going to choose a coordinate system aligned with the direction of the acceleration. So all of you with tension in your answer, nope. This is going to be the coordinate system I'm going to use. Next step, after choosing a coordinate system, break up any off-axis forces into components. All right. I've got one off-axis force. This angle has to be theta due to corresponding angles. And I will have a component of that force in this direction and a component of that force in this direction. This component will be mg cosine theta, and this component will be mg sine theta. All right. Net force in the y direction will be 0, and I'll make this the y direction. And net force in the x direction will be equal to ma. First semester physics. We're talking like October, beginning of October. We did problems like this. Only one of these has an acceleration, therefore only one of these has something that can be turned into a differential equation. So I'm going to probably work on this function. Based on my drawing, there's only one force component in the direction of x. So mg sine theta equals ma. All right. I believe the next step was to determine whether this is a restoring force or not. Does this force attempt to return the object back to its equilibrium position? Yeah. So if this is the positive x direction, then the acceleration seems to be positive, but my displacement would be negative. It's a restoring force. All right. Well, I have to write this as a second-order differential equation. So I'm going to do so. Well, this is why choosing this one is kind of hard, because I don't have x over here at all. And x represents the displacement of the mass. In fact, x would have to be this path, because that's the displacement of the mass. And I don't have it over there. But I think we can probably do something to get it over there. In fact, based on what we talked about just a few minutes ago, I could write that this length is equal to theta times L. But I don't have theta over there. I have sine theta. So for this example, I'm going to say, let's keep the angle small. If I do that, then I can rewrite this as negative mg theta. Now I'm just a hop, skip, and a jump from being able to work in x now, right? Take this, solve it for theta, and get x over L. So I'll do that substitution now. Yeah, sorry, the force one's harder because you got to work in something that has position in it instead of the angle. But we've done it now. We've done the work on that. So now our job is to collect constants and see if our system has a differential equal to a negative sign, a constant, and our position, our original function. So I've collected all the constants, and I've got my negative sign, I've got my position. This is a second-order differential equation that represents simple harmonic motion. That means omega has to equal the square root of mg over ml. Now, yeah, I know the m's cancel, so before you tell me that, just wait a minute. I want you to see something, and the top is supposed to be something about the restoring force. Does the top look like something about the restoring force? Yeah, this thing only works because gravity's pulling on it. The bottom should be something about inertia. Does the bottom look like inertia? Yeah, it's got an L in there, which I don't know why that's there, but it does have something about inertia, sure. So, truthfully, I can cancel out the m's, and when I do, I don't get that same satisfaction of having something on the top that's about restoring force and something on the bottom that's about inertia, because it doesn't look that way. But the holdover, where I started, definitely had the top had something about the restoring force and the bottom had something about the inertia. This is the controlling factor of a simple pendulum. And obviously it's controlled by both gravity and the length of the string. Not a surprise. For those of you who are interested, and some of you should be, if you want to do this using torque, it is easier. So before we actually launch into it, let's take a look at the torque. I don't need any of those things. I've displaced it in the clockwise direction of theta. All good? You guys see that? And there is a torque acting on it because there is a force acting downwards on the weight. That force is mg. So I believe there's an unbalanced torque that's going to cause rotational motion. So net torque equals I alpha. Torque has three parts: the length of the torque arm, the size of the force, and the sine of the angle between the torque arm and the force. So length of the torque arm, size of the force, and if I come down here and look, that angle has to be theta due to corresponding angles. Remember my geometry. So sine theta. This is a point mass rotating about a pivot point over here. So what's the moment of inertia of a point mass? So this will be ml squared times alpha. All right, let's write this as a second order differential equation. Alpha would be the second squared with the second derivative of theta with respect to time. Because alpha is d omega dt, and then omega is d theta dt. This is going to equal LMG sine theta. I will say that my torque is counterclockwise, even though my displacement is clockwise. So I'll put that negative sign in there to indicate this is a restoring torque. We're close, so I'm going to do the same small angle replacement here so that I'm not dealing with the sine, but I'm dealing with theta directly. And I'm also going to solve for the second order differential. Do I have a second order differential equation with a negative sign, a constant, and a displacement or an original function? Looks like it to me. Because of that, this has to be omega squared. So omega is equal to the square root of LMG over ML squared. Now, that looks a lot more like a restoring force and inertia. Doesn't it look like that to you guys? It still drops down to be square root of G over L, right? M's cancel and one of the L's cancels. But it really looks like we have something that has the restoring force in it, and we have something that has inertia in it. But yeah, square root of G over L. There, I've put a little help on the board. Will that be enough help for you to realize what I'm asking for you to do? I hate the idea of having to do it, but you have a whole collection of things now, all related to omega, and you have a new omega.